All right, so today we're going to do 7-8, which is dealing with improper integrals. And so all the techniques of the integrals that we've done in the past are going to come into play. But these integrals are actually quite unique in the fact that what ends up happening here is what makes them improper is that we're going to values of unknown because we're going to infinities in our integration. And so when we go into these infinities of integration, we don't have straightforward techniques for that. So we have to take limits of these values to be able to solve problems going forward. So this actually becomes quite a big stepping stone to eventually understanding chapter 11. So this is something that should be something that you understand and grasp well. I will post these notes. Ooh, I don't know if I did post these notes. I don't think I did. I'll post them up after class for you all, both the filled in and the empty ones. Sorry, I blew it. But you guys can read about the definition for improper type 1s. I want to do examples for you so that you can understand it, and then we can have a dialogue about these problems. Now, what ends up happening is when dealing with impropers, we end up trying to find out one of two things. We either find out if it's going to converge, and if it converges, that means that we have a numerical value when we take the limit. If it goes to infinities, we're going to have it being divergent. Okay, so I'll show you these, and we'll build from there. Okay. All right. Let me show you some examples, and then hopefully this shouldn't be too bad for you guys to grasp. All right, so in this first example, what we end up seeing is we're taking an integral that's going to go from 1 to infinity, and we need to determine if this thing is going to be convergent or divergent. Well, I told you since it goes to infinity, we don't have straightforward techniques for that, so we need to manipulate it using limits. And so it's going to be equivalent to this. So equivalent from 1 to infinity of 1 over x dx is the limit as t goes to infinity from 1 to t of 1 over x dx. This problem would be slightly different, and I'll show you that, if we were going from 0 to t. I'll deal with that later, because if we have it going from 0 to t, our limit ends up being, it'll be a little bit tricky, but I'll address that in just a bit for you guys. So then from here, we don't need to worry about the limit part. We're going to worry about the integration piece. So the integration of this is going to be the limit as t goes to infinity. And what is the integral of 1 over t? Or 1 over x?
Natural log absolute value of x?
Correct. So it's going to be the natural log of absolute value of x. And then we're going to We're going to evaluate that from 1 to t. Right? So then our limit is going to be as t goes to infinity of ln of absolute value of t minus ln of 1, right? But we know ln of 1 is 0, so that piece is going to be 0, and so we get the limit as t takes off to infinity of the natural log of t is going to be equal to what? So to help you, because I'm sure your limits have been a while, right? It's been a while since you did a limit. Let's look at what ln of t would look like. Wouldn't it look something like this? Right? What is the y value? In fact, I should make it, since we're talking about t, that's our input, here's our y. What would the maximum of this thing be? Where is it going to as I take off to infinity?
Wouldn't it just be infinity because we don't have any like...
That's right. It's going to be infinity. ln of x doesn't have a horizontal asymptote, and so this thing is infinity, right? Infinity isn't a definite number, so that tells me that this whole function is going to be divergent. Does that make sense? Since it takes off to infinity, it's divergent. It's not the movie. It's going to go without bound. And since it goes without bound, it doesn't go to a number. Okay? Is there any questions on this? It's a whole new concept, and I want to make sure that you guys are okay with it. Pretty straightforward?
Yes.
Okay, so notice we went to infinity. Because we were going to infinity, I changed the variable to t and took the limit of t going to infinity. So I can do this integral, it's manageable for me, and then when I evaluate, then I apply the limit. Okay, that's the technique to this type of problem. All right, let's do another one, slightly more complicated. I want you guys to be able to see these in a variety of ways. So let me do this one here. So now what's happening is I'm going from negative infinity to 0 of x e to the x dx. And so when we're doing this problem, now we're going to take the limit as t goes to negative infinity. It's the infinity that we're trying to go after. From t to 0 of x e to the x dx. All right, so now I can think of the t as a number, right? So this is something that I can handle. Now, how do I integrate x e to the x?
By part?
That's right. It's an integration by parts. And so it's actually the UV integration. So my u in this case is going to be x. My dv is going to be e to the x dx. So du is dx. V is e to the x. And so what's going to end up happening here is I'm going to get x e to the x minus the integral of e to the x dx, correct? And then I'm going to get x e to the x minus, gosh darn it, e to the x, but I have to remember that this whole thing is being evaluated from where to where. It's being evaluated from t to 0, correct? And so what I'm going to get is 0 minus 1 minus t e to the t plus e to the t, correct? But one of the things that we've left out is the limit as t goes to negative infinity, correct? Are you guys with me?
Yes.
Professor, why would it be plus e to the t?
Oh, why is this a plus?
Yeah.
Okay, so this minus sign here, right?
Yeah.
So when we do the fundamental theorem of calculus part 1 tells us if I go from a to b of f of x dx, the fundamental theorem tells me the integral, the antiderivative of b, minus the antiderivative evaluated at a. So there's a minus, right? So then when I do minus, this is going to become a minus. That's this piece.
Oh,
And then the negative with the negative becomes a
positive.
positive. It's
Yeah.
from the fundamental theorem of calculus part 2.
Yeah.
Right?
Okay. Yeah.
I think that's like 5.3, chapter 5.3 or something. But good to know. Okay, so then from here, when I evaluate this limit, I'm going to get -1. As I go to infinity, I'm going to show you this as a side work piece. I'm going to get -0 plus 0. And so my answer is going to be -1. So since it's -1, I know that this thing is convergent and it converges to an area of 1. But I'm sure that you guys probably don't remember your limit work. So I'll do this second one here so you guys can see it, because this second one will actually yield this one also. So watch this. The limit as t goes to -infinity of t e to the t. This looks like it's going to be problematic because I have infinity times 0, correct? It's infinity times 0. So I'm going to manipulate it so that I can see this problem. And my manipulation is going to be this one. So I'm going to go, all right, t over e to the negative t. That's the same as the first step, right? But now, when I evaluate this, don't I get -infinity over infinity?
Yeah.
Yes.
So infinity over infinity lets me do a thing called L'Hopital's rule, right? The Frenchman who stole the Bernoulli brothers' solution. He paid them for it. I guess he didn't steal it. He paid for it. So infinity over infinity lets me do L'Hopital. So I'm going to get the limit as t goes to -infinity of 1 over -e to the negative t. And we can see that's the same, and I already see what the answer is, but that's okay. The limit as t goes to -infinity of -e to the t, that is 0. Any questions on how I got that? None? Okay. So we can see, look, the limit as t goes to infinity, who cares about the negative, of e to the t means this one is also going to be 0. You guys see that? So by doing this one, I actually was able to do the other one also. That's why those are both 0. And we see that the integral from -infinity to 0 of x e to the x dx has an area of -1. So cool. We okay?
Yes.
Okay. Now remember, when is our exam? I want to stress that. When is our exam?
Next week, Monday.
Monday. So next Monday, we have our exam number 2. Woohoo! Isn't it exciting? All right. Let me go on to the next problem. Are you guys okay with writing this stuff down?
Yes.
Okay. Okay, so let's look at this next problem. Part of the deal with these problems that we're doing now is it's about comprehension, right? These problems are no longer these like rote, like, oh, okay, I have these steps, I follow these steps, I'm going to be perfect if I follow these steps. With these problems now, there has to be some understanding that occurs. And so as I explain this problem, please, if there's something you don't understand about my reasoning, you got to ask, okay? That's pretty much going forward in this class. The reasoning behind it has to be there. Okay. So let us go. So in this problem, in the first example, we just did it, right? The first example that we did in class, I showed you that if we have 1 over x, what did we end up getting?
Divergent infinity.
Infinity.
What did you guys say?
Infinity, but that it was divergent.
Yeah, so it's divergent. So we know that if p is 1, we're going to be divergent in this case. So we're not going to worry about p is 1. Okay? Because I did it. I won't say we know. I'll just say assume if p equals 1, we're not going to do p equals 1 because we know that p equals 1 is divergent, right? And I showed that. So we're going to do the cases going from 1 on. So this integral from 1 to infinity of 1 over x to the p dx is going to be equal to the limit as t takes off to infinity of 1 to t, and I'm going to do it this way. Now, do you guys know why I did it this way? Why did I make it x to the negative p?
Because that's equivalent to 1 over x to p.
It is. It's equivalent, but the reason I did it is because then from there I clearly see it's just the power rule. So whenever I can use techniques that I already know, I try to put it in that form so I can easily integrate. So this looks like a power rule problem. I can do power rule quite easily, correct? So what's going to end up happening is I'm going to get the limit as t takes off to infinity of x to the negative p plus 1 over negative p plus 1. And then I need to evaluate that from 1 to t. Agreed?
Agreed.
And that can be rewritten to be 1 over negative p plus 1 of, I'll do it this way, 1 over x p minus 1 minus 1. Does everyone agree how I went from that step to the next one? If you don't, please speak up. We okay?
Aaron's asking if you can show.
Oh, I didn't
what
see
exactly
it. Cool.
happened.
I missed that on the participants was blocking my chat. Okay, so cool, no problem. So what's happening here, and I'll show this work just so you guys can see it real quick, and then I'll erase it. When I plug in my my t value, I'm gonna get I can factor out 1 over negative p plus 1, right? Because that's just the denominator. when I plug in t, don't I get t to the negative p plus 1? And then when I plug in 1, aren't I going to get minus 1 to the negative p plus 1? Are we in agreement?
Yes.
Okay, any value that p becomes, that 1 to that power is going to become a, for any p value, what is this going to become?
Maybe 1.
1.
Yeah, 1.
It's 1. So I'm going to get 1 over negative p plus 1. And now if I bring this down, because I want the p to be positive, I'm going to go t to the negative p plus 1, right? Because power rule tells me if I go down, it has to become a negative, or if I go up, it becomes a negative, right? Minus 1. Well, doesn't that become 1 over negative p plus 1 of 1 over t p minus 1 minus 1? And that's how I got to that next step. Does that make sense, Aaron?
Yeah.
Okay. So that's what I'm saying. These little algebra steps, right? They can be devastating. So if you need me to show them, it's more than my pleasure to be able to show them to you guys. All right. May I erase that? Or should I leave it there for a little bit for people to copy? It's okay. I'll leave it for a second, and then when I need the space, I'll erase it. So then from here, ooh, I left out one thing here. Shoot me. It's the limit as t goes to infinity. I forgot to put that in. So what ends up happening here is I need, now I'm going to erase this. I need the space. I will need the space. So from here, there's going to be two cases that I need to address. I've already addressed, by doing that first example, p equal to 1, right? We know that if p equals 1, we're divergent. Now we're trying to deal with what happens when p is bigger than 1. So that's the case we need to deal with. So if p is greater than 1, this then tells me, then I know that p minus 1 is going to be greater than 0. Do you guys agree with that?
Yes.
Okay, good. Thank you. Your response is important to me. Now, this then implies, so as t takes off to positive infinity, my t to the p minus 1 is going to take off to infinity. Does that make sense?
Yes. Yes.
Okay. And from there, by that reasoning then, 1 over t to the p minus 1 has to go to what? What is that going to go to?
Infinity?
If infinity is the denominator, right? Because this is the denominator. If that's going to infinity, 1 over infinity is going to go to what?
Negative infinity.
Wouldn't it be 0?
It goes to 0.
Oh.
Right? Right? Because think about it. If I go 1 divided by 10, that's 0.1. If I go 1 divided by 1,000, that's 0.001. I skipped 100. But you see it's getting closer and closer to 0, right? So if the denominator goes to infinity, some constant divided by an astronomical large number is going to take us to 0, right?
Right.
In agreement? Now,
Yes.
since that is going to a fixed number, namely 0, what do you think happens to this integral? What do you guys think? We're going to get 1 over p minus 1 is our solution. This is going to be the actual solution. If p is greater than 1, and since it went to a fixed number, this tells us this integral is going to converge. Does that make sense?
Yes.
Okay. So we know that if p is greater than 0, we're going to converge. Now let's see what happens if p is less than 0. I know the question isn't asking us for that. It's going from 1 to infinity. But let's see what would happen if we were to attack this thing if p is less than 1, right? Our t is still going to infinity, but now our p is some fractional number between 0 and 1. That's the other case that we have to address. So if p is less than 1, right, because we have the three cases, greater than 1, at 1, and now less than 1, what's going to end up happening here then is we're going to have p minus 1 is less than 0. Do we agree with that?
Yes.
Is there anyone who's unsure why that's less than 0? Please be honest.
Yeah, could you explain it, please?
Sure, no problem. So think of it this way. If p is less than 1, let's say that p was a half, right? What's 1/2 minus 1?
That'd be negative 1/2.
Negative 1/2. Is that less than 0?
Yes.
Yeah. So any number that we put in there that's less than 1 is going to make this become a negative. That's all this is saying.
Okay.
Up here, if p is greater than 1, then this thing has to be a positive number.
Great. Okay.
Right? That's really what it's going after. But that reasoning is so important, because if you guys don't see that, then the rest of the stuff that I'm saying to you is kind of gibberish because the reasoning isn't there. Okay? So it's important. This is what I mean. Like, it's these subtle little ideas, but they matter. Okay, so then from here, we go, so 1 over t to the p plus 1, isn't that equal to t to the 1 minus p?
Yes.
Okay.
Yeah.
And where would that go as t goes to infinity?
As t goes to infinity?
Mm-hmm. Because p is going to be some fractional number, right?
Right.
So let's say a half, right? So 1 minus a half is going to be the root of t, right? But if t takes off to infinity, what's the root of an infinite number?
Well, it'd still be infinity, right?
That's right. So this thing's going to take off to infinity. Right? Because these things are going to be different roots. Right?
Right.
And so those roots are going to take off to infinity. Or if we end up in the negative realm, they end up being exponents that are going to blow up. This thing's going to take off to infinity. And remember, and just so you guys know, this will be as t goes to infinity. So what this ends up telling me is that if my value is going to take off to infinity, it didn't go fixed. Notice this one went to a fixed value, right? it would be bounded as t went to infinity to a bounded value. This guy is not going to take off to a bounded value. It's going to take off to infinity. So that tells me that the integral, if my p is less than 1, will most definitely diverge. So what do we know about this thing? It's a rule that we're going to have, and I want to write it down for you. If you're taking the integral from 1 to infinity with the p value, the exponential p, being greater than 1, we know it's going to converge. From 0 to 1, or when p is less than 1, less than or equal to 1, we know we're going to diverge. Okay? So here's the rule. The integral from 1 to infinity of 1 over x to the p dx is convergent if p is greater than 1. It is divergent if p is less than or equal to 1. This is a rule you should know. Now, if it's divergent, do you need to show a lot of work?
No.
No, not really. But if it's convergent, I'll be able to ask you for specific values. And that's what's going to eventually happen. I'm going to say, all right, this thing's convergent. If it converges, what does it converge to? Right? But you'll be able to tell me right from the get-go, does it converge or diverge? Well, if p is less than or equal to 1, in this case, diverge, work is done. If it does converge, then I'm going to ask, if it does converge, then what does it converge to? And then you'll be able to take the specific integral depending on what your p is. Understood? And that should be quite easy, because if p was 3 here, we see that 3 minus 1 is 2, and so my answer should be a half.
Okay.
Okay? All right. Let me go on to the next. So 1 over x to the p, right? 1 over x, where I did the integral, this thing was continuous everywhere, right? From 1 to infinity, 1 over x to the p is going to be convergent everywhere, or is going to be a continuous function everywhere, correct?
Correct.
Okay, that's important. Now we're going to play with things that are not continuous everywhere. Actually, yeah. We'll address that here, okay? So what ends up happening here is we need to address these potential issues, and when we deal with these potential issues with discontinuities, what we end up having to do is attacking them, either approaching from the left or approaching from the right. Does that make sense? Remember that from limits, if we had a right-handed continuous or left-handed continuous, you had to approach from the opposite side to be able to find the limit, correct? So that's what's going to happen here.
Yeah.
So let me show you an example of this, and then I think it will make these rules become quite clear to you. So let's look at this example. Okay, so looking at this example, we're going to go from 2 to, let me make sure I have that right. I think it's not supposed to be squared. I think I messed up. So let me confirm this real quick. I think I put a square there accidentally, and it will change the problem completely. Because this problem wouldn't have a problem at 2.
You did. It's the square root of x minus 2. It was your example 5.
Yeah. I think it's just x minus 2. So this is not squared. That's a mistake. Okay. So looking at this problem here, we see that we have an issue at 2. And since we have an issue at 2, the important piece here to understand is now we need to take this thing as a limit as t approaches 2. But how do we want to approach it? Do we approach it from the left or the right? There's the reasoning. Here, if we approach from the left, right, meaning a value smaller than 2, what happens to our radical?
It's undefined.
Yeah, well, it becomes imaginary, right? And we don't want to play in the imaginary world. So we need to come and attack this thing from the right-hand side. Okay? So this is the reasoning that's going on with these types of problems, and it's important that you all get this. So I'm going to go from t to 5 of 1 over the root of x minus 2 dx. Okay? And we can do this, this integral, right? We know how to do this integral. How would we attack this integral? What would you do? Am I putting you guys on the spot right now?
But you bring it up.
I mean, you could bring it up. That's totally fine, but that still doesn't help us. It's a U sub. So we would bring it up. I'll actually show you guys the steps just so you guys can have it. It's du is equal to dx. So I'm not going to worry about the limits. I'm just going to do indefinite. So I'm going to get 1 over u to the 1/2 du, which will then be the integral of u to the negative 1/2 du. And we know that this is u to the negative 1/2 plus 1 over a negative 1/2 plus 1, which would be, what is that? 2 u to the 1/2. But then we need to remember that that is 2 times x minus 2 rooted. And now we can bring our limits back in. Right? So then when we evaluate this, here I'll come up here. I'm going to get the limit as t goes to 2 from the right of 2 root 5 minus 2 minus 2 root t minus 2. Agreed? We know that the first one's just going to be 2 root 3 minus the limit as t approaches 2 from the right of 2 minus 2. Right? I don't want to direct sub yet. So when I direct sub there, don't I get 2 root 3 minus 0? Correct? So our answer ends up being 2 root 3. Since we have a specific answered number, what do we know about this integral?
It's divergent.
Not divergent.
Really convergent.
It's convergent.
Because we have a numerical value.
That's right. It's convergent because we have a numerical value. We know what the answer is. It's 2 root of 3. I probably wouldn't ask you that whether it's convergent or not, because having the fixed value tells you it's convergent. It's not going to be convergent when the limit does not exist or the limit goes to positive or negative infinity. Are we okay with that?
Yes.
Why did you pick approaching from the positive side in the limit? All right, Andrew, maybe you missed this when I first started, but it's okay. I'll say it again. So when I look at this, right, I see that 2 is a problem, right? Because if I have 2 minus 2, my denominator becomes 0. That's problematic. You agree with that? Okay. Now, to decide if I come from the right or the left, if I come from the left, isn't that going to be like 1.9, 1.99, and all of those? Agreed? Okay, so what's 1.9 minus 2?
Negative 0.1.
Yeah, it's a negative. And since it's a negative, a root with a negative becomes imaginary. We don't want to play that game. So we want to be positive. So we want to approach from the right because the values that we're going to plug in for x will be bigger than 2. Does that make sense, Andrew? Yeah, that's the connection to these problems. Knowing how to attack it because you understand the restrictions on the domain. Cool. You're good now? All right, cool. Thank you for asking the question. I must have not done a very thorough job. I want you guys to be able to get this and understand. Okay. Here's our next problem. So now in this problem, we see again we fall into an issue, right? We're going to go from 0 to 1, but ln of 0 is what?
Is it undefined?
Yeah, your calculator is going to go freaky on you, right? If you try to use your calculator, it's going to be like, error, what the heck, you know? Because ln never gets to 0. It gets really, really close, but it never gets to 0. So we have a problem in this problem with the domain, and the domain issue occurs at 0. Cool? So then from here, what ends up happening is now I know I need to approach the ln problem as I'm going to 0, right? So it's the limit as x goes to, I'm sorry, not x, I need to call it a different variable. T goes to 0, but which way do I want to attack it? Do I want to go from the left or do I want to go from the right?
On the right.
It's going to be from the right.
Right.
And part of the issue there is I know that I'm going from 0 to 1, so I should see that I'm coming from the right. But we also know that ln isn't defined on the negative side, so that wouldn't work for us, right? So we're taking the limit as t goes to 0 from the right, and our integral now is going to go from t to 1 of ln of x dx. We all know how to do the integral of ln of x now, right? Shall I show it just to reaffirm you all? Or can I just do
Please.
it? You want me to show it?
Yes, please.
All right, no problem. So here we go. So ln of x is a UV problem. So my u in this case is going to be ln of x. My dv is going to be dx. So du will be 1 over x dx, and my v is going to be x. Okay, so I'm not going to worry about the limit. I'm just going to do the integration piece, and then I'll apply the limit after. So I know that it's supposed to be uv, and I'll write the rule just so you guys know, uv integral of v du. So I'm going to get x ln of x minus the integral of dx, right? Because 1 over x times x is going to cancel. I'm going to get a 1, so it's just dx. So this is going to be x ln of x minus x. But now I'm going to apply the values. It's going to be from t to 1, and I need to remember that my limit is as t goes to infinity from the right. Agreed?
Agreed.
Okay. So then as I plug in my values, I'm going to get, well, I'll do this piece first. That should be a t, dang it. T goes to 0 from the right. I'm going to get 1 ln of 1 minus 1 minus t ln of t minus t. which should become a plus. Ln of 1 is 0, right? So my limit as t approaches 0 from the right is going to be 0 minus 1 minus t ln of t. Really, it should be an absolute value, but it won't matter. So as t approaches 0 from the right, I'm going to get the easy ones, right? I'll do the easy piece. 0 minus 1. This one, I'm going to apply the limit because I need to show this one, I'm assuming. Plus 0. Everyone agrees with the other ones, right? 0, the minus 1, and the last 0.
Yes.
Okay.
Yes.
Now, when I do the limit, and I'll do, this is just side work so you guys can see. The limit as t goes to 0 from the right of t ln of t, I see that I'm going to get 0 times negative infinity. Agreed?
Agreed.
Okay, we can't have that, so I'm going to manipulate it to be in an indeterminate form. I'm just going to write t, being lazy. Do you guys agree that that is equivalent?
Agreed.
Yes.
Yeah, okay, cool. So then from there, if I apply the limit, don't I get negative infinity over infinity?
Yes.
Right? So
Yeah.
that tells me then that I can use L'Hopital's rule, and I'm going to get 1 over t over a negative 1 over t squared. Right? And that's still, I got to keep the limit. I'll rewrite that. That's ugly. Can't handle. So I'll get the limit as t goes to 0 from the right of 1 over t over a negative 1 over t squared. That's the same as going the limit as t goes to 0 from the right of t, negative t, right? But if I plug in the limit there, what am I going to get?
Zero?
I'm going to get 0. So that tells me that this here is 0. And so what I end up seeing is the answer to this problem is negative 1. And since it's negative 1, what do we know?
It's a convergent.
It's conversion. Are we good?
Yes.
Okay. Now I'm going to show you one more example. And I'll talk about the reasoning behind this guy. Okay? So sometimes we can't do integrals because we don't have the tools to be able to do them. So because we don't have the tools to be able to do them, we need to do a comparison. Okay? A comparison to something that we do know. All right? So in this next example, we run into an issue because we don't have an easy way to be able to integrate this problem. So we need to be able to choose functions that are similar, but yet cause that will lead us to advantageous solutions. Okay? So in this example here that I have, I have the integral from 0 to infinity of e to the negative x squared dx. I'm trying to show that this thing is convergent. The problem is I don't know how to do an integral of e to the negative x squared. Okay? So that means I have to manipulate this problem and use something that's going to be beneficial for me. Okay? So here comes the game. I'm going to draw a picture real quick just so you guys can see. And I'm going to use two different colors. So when x is 0, I know I'm going to get a value of 1, right? And what happens is this guy's going to look something like this. Okay? This red one is the graph for f of x is equal to e to the negative x squared. Okay? The green one that I'm going to do for you is going to look like this. Okay? And the value that's important is that at 1, they have the same solution, and this function would have been e to the negative x, right? Now, what ends up happening here in this problem, and this is what's all these problems have been, the issues that they've had, as these guys go to infinity, do they actually come to a value, or do they just get really, 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 really close to 0?
Get really, really close.
Yeah, they get really, really close, right? So what we're going to try to do is we're going to use e to the negative x to be able to see if we can come up with something conclusive. Now, the integral, and this hopefully will make a lot of sense to you because this is the important piece to this. From 0 to 1, we know that this is a fixed area for the one in red, correct? That's very measurable, correct?
Correct.
And it's the same for e to the x, e to the negative x. That area from 0 to 1 is very measurable, correct?
Correct.
Now, we're going to compare going from 1 on. Okay? If I am able to show that e to the x, e to the negative x converges, it's got a bigger area than the e to the negative x squared. Do you guys agree?
Yeah.
Yes.
Agreed.
Okay, so if I show that this converges, by default, this has to converge as well. Agreed?
Agreed.
Okay, so now choosing a function that works for you, that's going to be the critical piece, right? It's going to be something that's going to be very similar to the function you're given, but it's got to be something that you can integrate. Now, if I had chosen a function that I could integrate, but the area of it was smaller than the area of the e to the negative x squared, it would not do me any favors, correct? I got to pick something that's going to have an area that's larger from where I want to integrate from. So that's the mentality and the thinking that you're going to have to do when trying to attack this problem, okay? So let me show you. So everyone agrees with me that from 0 to 1, we know both these functions converge, right?
Right.
Okay, so then I don't care about that piece then. I'm going to deal with from 1 to infinity. And I'm going to take the larger area function because it's one that I can handle and I can do. We're good? So then in order to attack this, I'm going to take the limit as t goes to infinity from 1 to t of e to the negative x dx. Right? We know, and I'll write the step just so you guys can see it. We know that e to the negative x is negative e to the negative x, where we evaluate it from 1 to t. Agreed?
Agreed.
Okay. I'll start working down from here. So then when I evaluate, I'm going to go the limit as t goes to infinity of negative e to the negative t plus e to the negative 1 right?
Yes.
Okay. So I know that e to the negative t is going to be e to the negative t, but what's going to happen to e to the, or negative e to the negative t as I go to infinity? What value does that go to?
When to go to 0?
It's going to go to 0. So this first piece is going to be 0 plus e to the negative 1, and so I get e to the negative 1 as my answer. Since it goes to e to the negative 1, that's the same as 1 over 2.718281828, blah, 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 right? Did it go to a specific value?
Yes.
Yes. Since it went to a specific value, what do I know about the integral from 1 to infinity of e to the negative t, or e to the negative x dx?
Convergent.
It converges. Okay? Now, if it converges, if the green converges from here to infinity, what's this smaller area going to have to do? It's going to have to converge. The larger converges means the smaller must converge. And so, therefore, the integral from 1 to infinity of e to the negative x squared dx must converge. Is that cool or what? You guys are like, oh, I got homework. I will put up the homework today for 7.7 and 7.8. I will give you a full week to do it also. Okay? And then you guys can, that way you guys are prepping for the exam for Monday. Okay, I'm going to stop recording here, and then I'm going to answer some questions for you guys on homework, because I'm assuming you probably have some homework questions, correct?
Yes.
Okay. Or do you want me to record the homework questions on here?
Yeah, can you?
Yeah, sure.
Please.
Okay.
Can you go up though? Like, I want to see the problem.
This one?
Yeah. So this one, all we were doing was proving that it's convergent.
That's it.
Okay.
So see how it says show that this thing is convergent? That's the only thing. Because we don't have the tools to be able to do this integral, so we needed to use techniques to find something that had a larger area that converges, and if the larger area converged, then this thing would converge.
I see. And what do you mean by tools?
What's that?
And what are the tools that we don't have? Like, what do you mean by that?
Oh, you don't know how to integrate this.
Okay.
Yeah,
But
the toolbox isn't filled with how to integrate that yet.
But will it eventually?
Eventually.
Further?
Not yet.
Okay.
Okay? If you have a TI-89, it will do it for you for definite values, and it can show you what that would be. But the math that's involved there those techniques you don't have yet.
Okay.
All right. All right. Do this. What do I want to call this? Now this is homework questions. Okay. What do you guys got for me? Oh, I should probably pop up the WebAssign stuff so I can look at that. Anyone have any questions?
Yeah, I gotta go look for them now.
All right. Well, hopefully I can do them right.
I'm sure.
Well, today, man, with my Math 33 class, I couldn't reduce a fraction. It must have been too early or something. I'm like, man, I'm sorry, guys. Trust me, I know how to do this stuff. I'm sorry. So I felt pretty bad. All right. So 7.5, right?
Montel, are you gonna be posting the notes for this?
Yeah. I'll post this up today. It'll be up by this evening, though. I gotta run around the world till about 7 o'clock, so it'll be up. Probably by 8 o'clock. Okay. Okay. No questions?
Yeah, I have one.
All right. Which one?
For 7.5, number 18.
Number 18. All right.
Yeah, it's I don't know if you can see it.
Yeah. So here's what I've got. 25 tangent inverse of x over x squared, correct? That's the example that I have.
Okay. Yeah, the only difference is mine says 27.
Yeah, it's just a numerical issue.
Yep.
So, let's see this problem. So in this problem, it's a product, right? And since it's a product, it's a UV substitution,
Right.
right?
Yes.
Does that make sense?
Yeah, it would be tan inverse and then 1 over x squared, right?
So tan inverse is that, and then your dV would be the 1 over x squared dx, right? And we can pull the 25 out, so that's insignificant, right? So then my du is going to be 1 over 1 plus x squared dx, and my v is going to be a negative 1 over x, correct?
Yes.
Okay, so then when I go to do this, I'm going to have the 25 out front. U times v is going to give me a negative 1 over x tan inverse of x right? Because the u times v.
Yes.
And then minus the integral of v du. So the minus is going to give me a plus. And so I'm going to get 1 over x times 1 plus x squared dx. Agreed?
Right.
Okay, so then from here what ends up happening is this first one we're essentially done with, right? So the negative 25 over 10 inverse of x over x is done, right?
Right.
We need to deal with the second part. So I'm going to deal with the second part. So that's going to be a partial fraction decomposition. So what's going to end up happening there is I'm going to get 1 over x times 1 plus x squared is equal to a over x plus bx plus c over 1 plus x squared. Do you agree with that?
Yeah. Well, can I ask why it's bx plus c?
Yeah, it's the exponent. This is nonlinear,
Okay.
so nonlinear to linear,
Okay.
right?
Right.
So there's where your problem comes into play. And then from here, okay, we're going to do, we're going to find, so we're going to get a times 1 plus x squared plus x times bx plus c. So I'm going to get a plus ax squared plus bx squared plus cx, right?
Yes.
But we can see from this we're going to get did I distribute this right? Yeah, it looks right. So I'm going to get a is equal to 1, right? Well, actually, let me do it this way, because if I don't do it this way, it may confuse all of you. I'm going to get a plus b is equal to 0, c is equal to 0, and a is equal to 1. Agreed? So I know a and c, I know b has to be -1.
Okay.
Right?
Yeah.
Okay. So now when I go to do this thing, I'm going to get, I want to rewrite everything. Negative tan inverse of x over x plus, I'm going to get this integral decomposed. So it's going to be 1 over x dx plus x minus 1 over 1 plus x squared dx. Ooh, I'm sorry, my bad. That should just be a negative x. Do you agree with that?
Yes.
Okay, so then from here, we can do this. This is going to be 25 negative tan inverse. What am I doing now? Over x plus ln of x plus, this is going to be a u sub. Dang. So here what I'll do to do that integral, I'm going to say u is 1 plus x squared. So du is 2x dx. So 1/2 du is x dx, right?
Mm-hmm.
So that takes care of that. So I'm going to have a minus 1/2 the integral of 1 over u du. So 25 negative tan inverse of x over x plus ln absolute value of x minus 1/2 ln of 1 plus x squared. Correct?
Correct. Okay. Yeah, I think I just forgot that the C. So.
Oh, the C? Okay, so well, let me finish this off just so you can see it.
Okay.
So 25 negative tan inverse of x over x. Let's go ln of x over root of 1 plus x squared, right? And really, I should have my plus c here because these are all indefinite. From here, I should have my plus c, right?
Okay.
And that will give us our problem. We also could have done this as a trig sub, but I think it's straightforward to just do it this way by partial fraction decomposition.
Okay.
But that's the answer. Cool?
Yeah. So well, just quick question. The 1/2 coefficient in front of the ln, that accounts for the square root, right?
Yeah, and it makes it go to the denominator.
Okay.
Right? The negative is log rules divide, and the half is the root.
Okay.
Cool. Anyone else? Crickets? People were like, we still have homework to do.
I had another one,
Okay.
but now I kind of think like it might be the same. It was number 23.
23. All right, let me see if I can find that. All right, 23.
Wait, were you still recording these homework questions?
Yeah.
Okay, cool.
Yeah. All right, so this is number 23, you said. So we have an integral of x squared root of 4x plus 1.
Yes.
Okay, so for this one, what I would do is I would go, all right, it's a u, and I would do my u is this root of 4x plus 1, right?
Mm-hmm.
But I want to manipulate it so that I can...
Right?
Huh?
You would square it?
Yeah, because I want to get to that, I want to get to the x squared piece, right? That x squared piece is going to become an issue. So I know that this is going to be du is going to be 4 over 2 root 4x plus 1 dx, which cleans up to be 2 over root 4x plus 1 dx, right? So then that means I have to multiply by 1/2. And that's going to give me my 1 over the root 4x plus 1 dx. Right?
Yeah.
But I have an x squared term there in the denominator. And so
Right.
I need to be able to figure out what that is. So that would be u squared is equal to 4x plus 1. So u squared minus 1 is equal to 4x. U squared minus 1 over 4 is equal to x. And you can see how this thing becomes something quite fun.
Yeah. Okay. Yeah, because for the first part, well, for other problems, I kind of just see they go from the u to straight u squared, and then they'll take the derivative, and then you get the du. So,
Yeah, we could have done it that way. You want me to do it
Okay.
that way?
Well, that's how I started it, but then when it came to after, I got a little, I guess, intimidated by how the integral came out.
Oh no, it shouldn't be too bad. Your integral ends up being, once you clean it all up, it should be something pretty clean. So do you want me to do it from this side to attack it?
If you could, please.
Sure. So I'll do it without solving for x. How about that?
Okay.
So if I do it here, and this is typically, it is something that people do. So you're going to get 4 dx, right?
Right.
So then you end up with 1/2 u du is dx. Correct?
Right.
So then from there, what you end up getting is when we do our substitution, that 1/2 u du is the dx piece, and then your denominator piece to get the x squared piece out, we still need to do the substitution for the x squared piece. Right?
Yeah, that's what. Yeah.
So you still have to do that piece to go get the x, but it cleans up. It's just algebra. Do you want me to show it?
Yeah, if you could.
Sure.
Please.
So with the substitution, I'm going to get 1/2 u du, right? That's just the dx piece, correct?
Right.
Then I have my u from the square root of u piece. Do you agree?
Uh-huh.
Now I need to do the x squared piece. So to get the x squared piece, I'm going to go u squared minus 1 over 4 is x. So then x squared should be u squared minus 1 over 16. Agreed?
Okay. Wait, so the top one
This has
square
got to be
itself?
squared. That's got to be squared. Right?
Right.
Okay. Or if you want, I can even make it so it looks cleaner. I could have done something like u squared minus 1 over 4, that whole thing squared. That may make that may look cleaner to you. Agreed?
Okay, yeah.
So,
Agreed.
so then from there, I'm going to put that in here. So I'm going to get u squared minus 1 over 4 squared. But what do we notice about this and this?
Well, those two cancel out.
They're gone. So our problem ends up being not too bad. I'll have the 1/2 outside. So I have 1 over, let's say 1/16 u squared minus 1 squared du. But 1/16 in the denominator is same as multiplying by 16, correct?
Right,
So
so
I'm
it'd
going to
be
get
8.
8 over this,
Yes.
right? And so
Right.
I'm going to show you how to do the partial fraction decomposition piece here. It's a difference of squares inside, right?
Yes.
So I can go u minus 1 squared times u plus 1 squared du. Agreed?
Yes.
And so from here, I'm going to get a integral of, well, I'll just do the partial fraction piece. It's going to be a over u minus 1 plus b over u minus 1 squared plus c over u plus 1. Oops. Don't need that. And then plus d over u plus 1, that quantity squared.
Oh, shit.
Does that make sense?
Well, why do you, well, you know how you wrote u minus 1 and then u minus 1 squared separately?
Correct.
Well, why?
Yeah,
what would?
Yeah, when I lectured on this, these are called repeaters. So you need to do the repeaters.
Okay.
Because really what that is u minus 1 times u minus 1 times u plus 1 times u plus 1, right?
Right.
And so to be able to get those common denominators, or to do the decomposition,
Okay,
you
you
go
need to
from lowest
multiply.
power up, correct?
Right.
Yeah, and then from here, once you do all your cross multiplications and things, you're going to go solve for A, B, C, and D.
Okay, and then from there you do like the system of equations.
Correct. Correct. Does that make sense?
Yes.
Okay.
Yeah, I guess I just got confused when it came to breaking up that u squared minus 1 squared.
This piece?
Yeah.
Okay.
Well,
To here.
that's where I got stuck.
Yeah, because this is a difference of squares. And so see if you can factor the difference of squares to reduce the power so that you're not nonlinear.
Yeah, that didn't even cross my mind.
Yeah. No, and that's part of it, right? It's just practice. So one of the things is I figure probably some of you need more time on this homework. Is that a fair assessment?
Yeah, I had actually requested an extension. I don't know if that came up.
No. So yeah, I can do that right now. I'll give everyone extensions to Wednesday. That way, if you guys have questions on Wednesday, I can go over like some sort of practice test, but then answer further questions you might have on this section.
Okay.
So what I'll probably end up doing is just, instead of granting everyone extensions, I'll just extend the assignment to
Wednesday.
to Wednesday.
Okay.
Okay? Now from
All right.
here, can you do the breakdown of this, or do you want me to break it down?
Give me a. Okay, so like for the A, would you multiply it times like just the u pluses,
No.
or would you?
No, because it's not to the right. It's not to the right power, right? So, a, dang it, a would be multiplied by u minus 1 because it needs a u minus 1, right, to have the denominator to the right power, and then u plus 1 squared.
Okay.
Right?
Right.
Plus, then the b only needs to be multiplied by u plus 1 squared.
Okay.
The c would need a u plus 1, but then it would need u minus 1 squared. And then d would only need the u minus 1 squared.
For C,
Uh-huh.
it it would be u plus 1, not the u minus 1.
So it needs u plus 1 because look at it. Right here, what power u plus 1 is this? It's only to the first. The common denominator for all of this is going to be u minus 1 squared and u plus 1 squared, right? So this has a u plus 1, but it needs a u plus 1, and it needs the u minus 1 squared to it.
Okay.
Does that make sense? So the way that I would write it so you don't get confused is do this. Go a u minus 1, but since the common denominator is this one, right? What do I need? I need a u minus 1, and I need a u plus 1 squared. Well, what wasn't in my a? U minus 1 and u plus 1 squared.
Okay, good.
Does that help?
Yeah, I see it.
Yeah. And then on the b one, you have your u minus 1 squared. You need u plus 1 squared. So then you got to multiply by u plus 1 squared. For c, you have u plus 1. You need a u plus 1, but you also need u minus 1 squared. So I need u plus 1 and u minus 1 squared. Do you see that?
Yeah.
Yeah. And then obviously the d would be the same thing. I'll leave the rest of it to you from there, but that's how you attack this problem. Does that make sense?
Yeah, it does.
So the crux to this problem really was at the end, we still needed to go after the square, right? We needed to go after what x squared was.
Right.
Yeah.
Okay. Yeah.
Dan is right. These problems, I told you guys, it was a heavy lift. When I told you that this was going to take some time, if you waited till the weekend to try and do this, this was hours of work.
Those hours of work, not even waiting till the weekend.
No, for time. Well, that's what I'm saying. This was going to take some time.
Oh yeah, for sure.
So, yeah, because it's every technique that we've done, and then understanding. Wait, what technique do I use? This was going to be something that was going to take some time.
Yeah.
In fact, what I may even do is I may even extend this one till the exam, so you guys have time to be able to do the homework. But then you better do 7-7 and 7-8 with it. Okay? But this is a lift. There's no denying it. It's a lift.
Yeah, it's a lot of tricks to remember.
Yeah. So my advice is on tomorrow during my office hours and on Thursday during my office hours, hop on and get some help. Because this is going to take some work. Okay?
I haven't got to your office hours yet, but it's just like a Zoom link.
Yeah. It's in the, if you look in the modules, there is a Zoom link straight to my office hour.
Oh, okay, sure.
Yeah, so it's there. Just go in the modules. It's in the same thing as the recorded lectures. It says office hours in the tab. All right?
You know how
And
you showed us how to use the Piscus or the net tutor?
Oh, yeah, that's easy. All you have to do is click on there, and then if you click on there, I think all they ask you for is your email. I don't even know if they ask for that.
Yeah, but every time I hop on, it's like there's no room, there's no special, and like you kind of have to create your own. And then I don't know, it was kind of confusing for me.
Oh, weird. There's supposed to be people on there all the time. I will look into that, and I'll get back to you. Okay, Jason?
Okay, cool. Thank you. And then I had a question on 25. It was like first step. If you can just check that one out.
Sure. 25.
Yeah.
Okay. So this one I'll just put ... And you said 25. Let me look that up. All right, here's number 25. So we have the integral. My problem has 5 over x times x to the 4th plus 7, that quantity. That's what I have.
Yeah, and my question is, why did they like, I see what they did. They multiplied an x over x, which is just 1, to get the x squared when you do the u sub, you know, so you can substitute the x in the denominator would turn into x squared, and then you're going to u sub an x squared out of the x to the 4th power.
Mm-hmm.
And then you get the 5x because you're left with the x dx at the end of your u sub. But like, what made them want to multiply by x times x, which is just 1? Yeah.
Oh, okay. So the purpose of doing that was to be able to do a u sub.
Yeah, I didn't see it until the end, but then I was like, damn, I didn't know I was supposed to like think about that, you know?
Yeah, because what ends up happening is if you would have just said, let's say you would have done like, okay, my u is x, right? You're going to get dx. Well, what does that do for me? It puts me right back in the same position.
Yeah, because you still have x.
Yeah, so that doesn't work. So since that didn't work, let's say that I did x squared, right? But there's no x squared there for me to be able to like see anything. Does that make sense? So
yeah.
I needed to create something that would work. Now, typically, you guys would have probably done this as your initial guess, right? And then gone, okay, I have x to the 3rd, 4x to the 3rd dx, right? And so you would have gone 1/4 du is x cubed dx, right?
Mm-hmm.
And you could have done it this way, but the thing that sucks is when you do this, you'd have to take the cube root. And how do you take the cube root of a du? So you end up stuck. So what ends up happening here is we need to be able to create something that will help. And sometimes what that means is not changing our problem at all, but changing it completely. Do you see that?
Yeah, that completely changes it, yeah.
Totally.
And makes it solvable.
Yeah.
Wait.
Once you do this, I mean, look how simple the problem becomes. There's 2x dx. I have 1/2 du, which will give me that x dx. That eliminates the x dx.
Yeah.
And now everything is in terms of u. So that's the crux to this problem.
Cool. That's all I needed. I just needed you to like.
Yeah, because what ends up happening is you see how I try to go those other methods, and those other methods just led me to a dead end.
Yeah. Okay.
All right. Anything else? Do you guys want time to go do homework? Do you need time to go do homework?
Yes. I need plenty of time.
All right, here, let me, in fact, while you guys are here, let me change this schedule thing for you guys. In fact, can I stop recording?
Yeah.
All right, let me.
You said you were going to upload the notes, right?
Yeah. Here, let me stop recording, and then I'll set all this stuff up for you.